Change detection can be done with something called change vector analysis. And here's how that works. If you have an image with a couple of bands, you can plot a value of any given pixel on a graph like this one. These can be the original bands, or it can be indices you have derived from the original bands. In this example, I'm going to use some indices. For example, we could say that we've calculated NDVI for our image, and we've maybe used some thermal bands to calculate surface temperature. This is done for each pixel in the image. As you know, NDVI ranges from -1 to +1. And although surface temperature can have a very wide range, what we want to do if we employ change vector analysis is we want to normalize it. So we can say we have here an index that is a function of temperature that also runs from -1 to +1. This will help us calculate good magnitudes later. So if we have an image, for each pixel, we can plot its NDVI and its index of temperature value somewhere on this graph. Let's say the pixel that we're interested in has a value up here. Then we do the same for another image that has been acquired later on. The idea, because this is change detection, the idea is that we have two images that are acquired, one before and one after the change. So if we have our before image up here, and our after image, maybe the pixel has a different value of both NDVI and surface temperature. We have our after pixel here. What that allows us to do is to draw an arrow between the before and the after image for this pixel for these two values. And this arrow is what we call the change vector. So what does this tell us right now? It tells us that something happened between the before and the after images that led to an increase in NDVI and a decrease in temperature for this pixel. This would typically happen if we had a partly vegetated area where the vegetation grew. We would get more vegetation, especially if we get a lot of trees in an area, they will tend to cool that area down. So we'll see a decrease in temperature and an increase in NDVI. What we can then do is we can plot this kind of change vector for each pixel, and it gives us two pieces of information. The length of the vector gives us magnitude of change, and the direction of the vector gives us an indication of the kind of change that has happened. It doesn't tell us exactly what happened, but it gives us some kind of indication. So these two pieces of information together can tell us something about whether the pixel has changed or whether it hasn't. It's very rare if we have a before and an after image. It's very rare to have a pixel that has the exact same NDVI value and the exact same surface temperature value in the before and the after image. There's always something that's happening. But we want to typically separate little changes that don't really matter from the big changes that do matter. For example, if a forest has burned in the past and it's regrowing now, that's the kind of change that matters. But if the wind blew from the east in the before image and from the west in the after image, that's the kind of change we typically don't want to detect. So to try to separate those two, we have to define a threshold for the, sorry, I just realized I misspelled magnitude. We have to apply a threshold to the magnitude of change, where we say change magnitudes that are smaller than the threshold, those we don't really care about. They probably represent no real important change. Whereas those pixels that have changed more than our threshold, those are the ones we actually care about. We can visualize these as a circle, for example, around the before point here, where we say any change vector that does not escape this circle, we're going to ignore it. We're going to say this pixel hasn't changed. So that's how we deal with the magnitude. This typically ends up in a binary system where we have no change versus change. The direction can be a little trickier, but a simple way of doing it is to divide the directions into 4 quadrats. So we can envision those, again, based on our before pixel here, and we can label them, for example, A, B, C, and D. So in this case, we have a magnitude that is greater than our threshold, and we have a direction that goes into quadrat B. And quadrat B is the quadrat that leads us to increased NDVI and decreased surface temperature. So again, this doesn't tell us exactly what happened to the pixel, but it tells us the kind of change that happened. Some kinds of environmental changes have typical patterns. So we could imagine, for example, if a forest had been logged between the before and the after image, we would see a decrease in NDVI because we have a decrease in vegetation. And because a logged area tends to get warmed up more by the sun than the top of a forest canopy, we would see an increase in temperature. So this is the kind of change that's consistent with logging. We would get, if we see real logging, we would see a magnitude of change that's greater than the threshold and would see a direction going into quadrat D. That doesn't mean it's necessarily logging, but it's consistent with logging. We could also imagine we had an area near a river that got flooded. Because water has very low NDVI, that would cause a decrease in NDVI. And because water is typically colder than its surroundings, it would also create a decrease in temperature. So this is the kind of change that would be consistent with flooding. We would see a change that's greater than the threshold, and it would have a direction that's into quadrat C here. This kind of approach avoids some of the problems that post-classification change detection has with misclassified before and after images, which makes it a little more stable. It's still relatively simple. It's just based on 2 images, and it gives you a good indication of which pixels have changed and less direct information about what exactly the change was, but it does tell you about the nature of this change. The last thing I want to mention is that I've drawn an example in which we used 2 indices here. The reason why it's important that the indices have similar scales is because we need to calculate the magnitude of the change vector. And we use this with simple Euclidean geometry. And if we have values with very different ranges, for example, if we had NDVI, which ranges from -1 to +1, and we have surface temperature in maybe degrees Celsius that ranged from 10 to 40 for the image in question, it would be the magnitude of the temperature change that would dominate the total length of the change vector. So we don't want that. We want to have similar value ranges along both axes. You can also do change vector analysis with more than 2 variables. So for example, you could imagine if we had also calculated urban surface index, for example. You could imagine that we had another axis that points in or out of the screen, also with values ideally ranging from -1 to +1, and we would have a 3-dimensional change vector that we would calculate the magnitude for. In this case, magnitude calculation is very straightforward still. Now, of course, instead of having 4 quadrats, we would have 8 quadrats, because we would have these 4 both for increases and decreases in our third index. So translating the direction of change into something informative becomes a little bit more of a challenge once we start to add dimensions to this. But we could, in principle, add a 4th, a 5th, a 6th dimension as well. This makes change vector analysis a very flexible tool. It's often one of the first things that people try out if they have 2 images that they want to detect change for.